A vaccine scientist and an attacker can ask an AI for the same facts. The answer that saves a life can also help build the threat. Now imagine training that AI once, locking the dangerous knowledge inside the removable part and deciding afterwards who gets the key. That problem is bigger than virology. It appears in cybersecurity, nuclear physics, and specialized code that should never leave one company. Today's choices are blunt. Give the whole capability to everyone, give it to nobody, or build a different model for every kind of user. But computers already know a better rule. A guest does not get root access. People get only the permissions their job requires. The safest AI version of that rule is separate training. Remove the dangerous material and train a clean model for each access level. It works, but 5 versions means 5 full training runs. The paper asks whether one run can produce all 5 without leaving the dangerous knowledge everywhere. Most deployed fixes are cheaper. Teach the model to reuse, filter its answer, or put a classifier in front. Those guard the exit. They change what you hear, not what the model still knows behind the guard. Unlearning tries something stronger. It reopens a finished model and attempts to erase one capability. But a few hundred examples can bring the capability back because the knowledge was suppressed instead of cleanly separated. In the paper, the method that looked best at forgetting became the easiest to recover from when a mild attacker fine-tuned it. So editing the model after training is the wrong battlefield. The stronger question is whether training itself can control where each lesson is stored. And here's the trick. The dangerous text may travel through the model while the learning it creates is prevented from spreading everywhere. Each layer keeps a large shared core, then adds a small removable module for every subject you may later restrict. The output is simply the core plus whichever subject modules are switched on. The core never switches off. There is no learned gate making secret decisions. The data label chooses the module, which means the access rule stays visible and audible. Crucial move happens during learning on the signal traveling backwards through the model. Training makes 2 trips. The forward pass produces an answer. The backward pass decides which internal parts should change. For virology, the text travels forward through both the shared core and the virology module. On the return trip, the virology module always learns. The shared core learns only on a controlled fraction of those examples. That fraction is the dial. Turn it up and virology spreads into shared knowledge. Turn it down and the lessons stays isolated. So the method does not control what the model sees. It controls where the consequences of seeing it are allowed to land. And after training, remove the virology module. If routing worked, the general module keeps its abilities while the restricted capability leaves with the module. But that last sentence hides the hard part. How do you prove the knowledge did not leak into the core? A raw loss such as 2.71 cannot answer that for a human. The paper turns it into something we can feel. First, train an ordinary model and record how its loss falls as more compute goes in. Now place the modified model's loss on that curve, then read down to the amount of ordinary training needed to reach it. The answer is a compute ratio between 0 and 1. And it estimates how much training the model effectively received on that subject. 1 means full knowledge, and 0 means the model behaves as if it never trained on the subject. That gives us 2 clean tests. Did the model retain the safe knowledge, and did removing a module erase the restricted knowledge? The first test uses 2 million children's stories across 48 topics, with 4 topics treated as restricted. On everything it should retain, 1 modular model scores 95, 5 separately filtered models score 96, and that is essentially a tie. On the topic it should forget, the modular model scores 61 against 65 for filtering, and lower is better, so it forgets slightly more. The important number is not 61. It reached that result in 1 training run instead of 5. Then comes the realistic test. An 800 million parameter model learns web text, papers, and code across 4 restricted domains. The pattern holds. 1 modular run matches 5 filtered runs on retained and forgotten knowledge at roughly 1/5 of the training compute. 4 removable modules also create 16 access profiles. Even a combination never used during training works when those modules are switched on together. The messier text is more revealing. Label only half the data and filtering's forgetting score worsens to 85. The modular model stays at 60. Then scale makes that result stronger. From 50 million to 5 billion parameters, the forgetting cap widens instead of collapsing. And finally, the results come with 3 important limits. First, no method wins every metric. Better forgetting can cost general ability or make recovery attacks easier. And second, somebody still has to label the restricted data. The method moves that hard problem. It does not solve it. And third, the largest model was trained only once and one result was anomalous. The authors showed it as a dotted line and flagged it clearly. And even with those limits, the central idea holds. For decades, we controlled what models were allowed to read. Gradient routing asks a deeper set of questions. Where should each lesson live? Who gets access? And can we remove it later? If this helped and you want more like this, please consider subscribing.